The topic I wanted to talk about a little bit was interstellar material within the solar system. And so I guess the first question is, why should this group care about interstellar material within our solar system? We're trying to go to the stars. And I would argue that this group should care because if we can find material in our solar system, we can get a preview of the type of material we might be finding, the composition of that material. We might learn a little bit about the kinds of processes going on, and so it might actually be useful. So when I think about it, I try to think, I'm a planetary scientist. I'm grounded in this solar system. So what kinds of interstellar material can I think of? And I can think of three fairly readily. The one that's been studied the most are presolar grains that have been studied within meteorites. We've also studied interstellar dust with spacecraft. And then there are some, what I would call macroscopic interstellar objects that we have studied with telescopes. So I'll go through and talk a little bit about all three of those and what they might be able to do to inform the idea of going to another star. So we'll start with presolar grains. There have been something like 20,000 of these studied by now, a fairly large number. The story of how we got there is kind of interesting. It started with finding isotopic anomalies in meteorites, finding isotopic patterns in elements like xenon and neon that couldn't be explained by radioactive decay or other processes that we knew of. It took about 25 years to go from this is an anomaly to actually this is what it is. And it's a kind of an interesting story. One of the key figures is a chemist at the University of Chicago named Ed Anders. He was convinced that one of these anomalies actually was from a radioactive decay. There was decay of a super heavy element. There was a prediction that there were some stable, semi-stable super heavy elements with, number 110, 115, something like that. This was back in the 60s. He was convinced that he'd seen the decay product of fission. There was a faculty member at the University of Missouri at Rolla who was convinced that the guy at Chicago was wrong. Anybody in their right mind would bet on the chemistry professor at the University of Chicago, and he was wrong. But he was the one who figured it out. And one of the main things he did was to chase after this stuff by really what he was doing was burning down the haystack to find the needle. The reason I say that is meteorites are mostly made out of silicate rocks, rocks based on the silicon-oxygen tetrahedron. If you take those rocks and you put them in some hydrochloric acid and let's throw in some hydrofluoric and maybe some nitric, and you dissolve all the silicate rock, the anomaly is still there. The little fraction of material, a tenth of a percent, still has all the atoms of xenon and neon that were weird in the first place. So what is that? And this whole process, evolved over 25 years. It turns out that these grains are small. Some of them are literally nanometer size. The biggest ones are micron size. And the ones that Ed Anders was chasing are carbon rich. That's why all these things that went after the silicates didn't touch them. The first ones to be found were things like silicon carbide, graphite, diamond. Are also, silicon carbide and diamond certainly are very tough mechanically as well. If the images here are silicon carbide grains, notice there are scale bars on there. These are sort of a micron and down. Later, knowing what we were looking for, we can go after the more common materials in meteorites by just mapping on a section, a polished section of a meteorite, and just looking for isotopic anomalies once we had techniques that could analyze at the submicron scale, like the secondary ion microscope. So a little bit about these, where they come from. I love this plot. This is the two stable isotopes of carbon, their ratio plotted against the ratio of the two stable isotopes of nitrogen. And in the middle of the plot, you may not even be able to see it, but there's a little kind of greenish box. That's where everything on Earth falls. On Earth, the measurements are usually talked about in per mil, parts per thousand. Notice that the scale on this is thousands. There's a huge variation compared to what you see on Earth. And why is that? Well, one of the easiest ways to understand it is down in the lower left corner. There are a bunch of points with an N. Those match the predictions for chemical synthesis in novae. Well, then you think, okay, I can match the carbon and the nitrogen in novae. What about the other things that are predicted? And the other things that the models are good, yeah, they match. Well, what about the ones where they aren't good? What about germanium or krypton, or name the element that you want to? Then you can go look at these grains and see what those are doing. The rest of these things on here are a variety of different types of grains. They are mostly separated by first they were separated by their isotopic patterns, but it turns out they're separated by their origins. Most of these are from things like red giant AGB stars, supernovae, various things like that. These are basically grains that were condensed in the outflows of dying stars, one way or another, late stage stars. And then somehow they ended up in the solar system 4.567 billion years ago as things were forming, and they got incorporated intact into these rocks that became meteorites. It's really pretty cool that you can study the interior of a star in the laboratory. This is a technical triumph. It has a huge scientific payoff, but they really don't tell us much about other planetary systems because, these are grains that are formed after the star is dying. Okay? We're probably after the stars that are actually still doing fusion. Okay, next comes interstellar dust. This was discovered by the Ulysses spacecraft in the 90s as a stream of particles coming into the solar system. Now, it's not a very big stream, as we'll see in a minute. There were more detailed measurements by the Cosmic Dust Analyzer on the Cassini mission at Saturn. Again, you could kind of tell that these were the interstellar ones by the direction they were coming from. The Stardust Comet Dust Sample Return mission had made a real effort to return some samples of interstellar dust to analyze in the laboratory, and we'll talk about that as well. Here's a kind of a plot from the Cassini Dust Analyzer, and this is basically each point. That's kind of all they saw in their, 15 years. There aren't a lot of these things, but note that don't worry about the y-axis. It's basically radiation pressure, but the x-axis is the mass. Note that it peaks, or that it tops out at about, 10 to the minus 15 grams. That's a picogram. These are not big. There might be a few. Their analyzer would have been less sensitive to higher mass particles, and they concluded there were probably a few higher mass, but this is where most of these guys are. They could measure chemical composition, roughly, major elements, and found that the ratio of the elements like iron, magnesium, silicon were in chondritic or solar system average proportions, but carbon was depleted. We're looking at picogram-sized rocks, not ices. Okay. The Stardust mission tried to capture these in aerogel. The aerogel, I don't know if you're familiar with that, but it's got a density of 1,000th that of water, something like that. You can slow down a fairly high-speed particle. They were mostly worrying about things going at a few kilometers a second from Cometville 2. But on the backside, they would occasionally turn their spacecraft so that they should be able to catch this stream of interstellar dust. Now, they had a collector this size, and they are looking for on the biggest image, there's actually an arrow toward a track from one of these. The tracks are micron size. That's more than the scientists wanted to do. They set up a citizen science project called Stardust at Home, where they did automated photographs of the whole thing, automated images, and then had 30,000 individuals doing 30 million searches, and they found 69 candidates, most of which they could tell from the trajectory came off the spacecraft. 2 of them were consistent with being interstellar. The scientists went and found on the foil connecting the aerogel, found 4 more craters that could have something interstellar in them. But these are small enough, and capturing an aerogel degrades them enough that only basic measurements, like, it's coming from that direction, were possible in maybe 1 or 2 elements. So in summary, again, this is a technical triumph. These can tell us something about the processing of grains in the interstellar medium. It is actually relevant to what we're talking about in that it tells you something about the stuff you're going to run into when you're going between here and the next star and what direction that stream is going. But again, it doesn't tell us much about other planetary systems. So that brings us to the most recent kind of interstellar material discovered in the solar system, that what I call macroscopic interstellar objects. The first one, which we've already heard mentioned at least once, is called Oumuamua. It was discovered just a little bit over 2 years ago. Every telescope that could be pointed at it was pointed at it, but not for very long, because within a week it was a factor of 10 down in brightness. Within a month it was down by a factor of 100, and quickly faded from all but the biggest glass. A little bit about the name. This was discovered at this telescope in Hawaii. Do we have anybody? I don't think we have anybody Hawaiian here, do we? Okay, we have some Hawaiians. Then, okay, if I mess up the pronunciation, you can correct me. But I did see that there was one slide earlier in the week that misspelled Oumuamua because it left off the consonant at the start of the name. The consonant is called an okina, and it's actually one that's sometimes used in English, but I know of only one word. That's the word uh-oh. It's that glottal stop in the middle. So, and it was given the title 1I. They couldn't decide whether to call it a comet or an asteroid or what. Then they realized, oh, it's interstellar. So it's the first interstellar object. So it's 1I. A little bit of the detail. When it was discovered, it was 6 weeks past perihelion. And it was quite a perihelion. It came within 1/4 of an AU of the sun. That's inside the orbit of Mercury. When it was discovered, it was roughly at its closest approach to Earth, which was 1/6 of an AU. Again, pretty close. The eccentricity, that's the key thing for understanding that it is truly interstellar. Remember, an eccentricity of 0 is a circle, 0 to 1 is an ellipse, most orbits. Then greater than 1, it's outward bound. Well, the first analyses said that this looks like it might be greater than 1, but there are comets that leave the solar system because of outgassing. They get some non-gravitational acceleration, and they end up accelerating to greater eccentricity greater than 1. But this thing, that's well over it, and we didn't see much non-gravitational acceleration either. Some other things about it. One of the most spectacular things was the light curve, basically measuring how bright it is with time. And the main thing you see there, this is reflected light, reflected sunlight. And to give an example, if you have an object and it's rotating, how much surface area it presents to you changes with time, particularly if it's a kind of a weird orientation. Oumuamua, the variation, the scale on the y-axis is astronomical magnitudes, which are a factor of 2.5. It's a log scale. And you actually can't quite see the top of the brightness here, but this thing varies by a factor of 10 in brightness. The calculations are that the aspect ratio is something like 6.5 to 1 or more. The average dimension was concluded to be something around 70 meters, but really this is more like 100 meters by 20 meters or something like that. So get an idea for that scale. So what is it? Asteroid? Comet? What is it? In one sense, it would be easy to call it an asteroid. None of the telescopes saw any evidence of any gas or dust coming off of it. It was star-like. It looked like an asteroid. Except, comet, well, people expected the first interstellar thing to be discovered to be a comet. For one thing, they're the things hanging around on the outside of a system that can get ripped off and moved around. For another, they tend to be giving off dust and gas, which makes them easier to see. Oh, but wait a minute. This didn't give off dust and gas. But it did have non-gravitational forces. It did accelerate by other than gravity during the course of people watching it, although the calculations were that the amount was consistent with an amount of outgassing of water that would not produce enough to see with a telescope. Okay? The spectrum of Oumuamua looks very much like stuff in the outer solar system. No features of titanium from the paint or anything like that. So, I don't know. What is it? The second interstellar object, okay, in a lot of ways, this is easier to understand. This one looks like a comet. It's 2I, the second interstellar object, Borisov, discovered a couple of months ago by a Russian named Gennady Borisov, working in the Crimea. Figure out whether you want to call him Russian or Ukrainian or what. It has not reached perihelion yet, so we will be learning much more about this object. So here's the cheat sheet on it. It was discovered in August. It reaches perihelion a little less than a month from now. So it will be getting brighter. But the perihelion is only 2 AU from the sun, so it's farther out than Mars. Although new comets coming in from the Oort cloud have been known to break up at that distance when they have perihelion there. So it may yet break up. We don't know. Now, the eccentricity, remember I said, Oumuamua, it was a little bit questionable. Is this really interstellar? No doubt about this guy, eccentricity of 3. And of course, that does mean, its velocity coming in was, 32 kilometers per second, moving pretty quick. This one doesn't get very close to the Earth, only a couple of AU, but it's giving off this dust and gas, so we can kind of look at it. So, it looks like a comet. Is it a typical comet? First molecule detected was CN. That's normally the first molecule detected in a comet. So far, so good. The next molecule detected, C2. That's normally the second molecule detected. In fact, comets are classified based on the ratio of C2 to Cn. And there's enhanced and typical and a little bit depleted in C2. And this measurement by Coretta et al. Puts it in the depleted category, but well within the solar system measurements. And then a week later, there was a measurement saying, no, we can't see it. We only see an upper limit. And in fact, the C2 to Cn would be guaranteed to be below virtually all comets in the solar system. Although, when I looked at this, which was about the time when I was writing up the paper, I realized that isn't, here's the upper limit. It's not that different from the lower error bar of Coretta et al. And then a week later, I talked to Teddy Coretta, who is a graduate student in our department, who said, we looked at it again, and we don't think we see C2 anymore. So it is low. And by the way, I'm not trying not to throw Teddy under the bus because he wasn't actually the one on the paper who did the analysis that said they got it. But so now this does not look like anything we've seen. It's really low. Okay, now what? Well, next thing detected was not water, but some oxygen, an oxygen phase that is often produced by water. And if that's right, then the CN to water ratio is in the typical range. So, is this typical? I don't know. Oh, and I should mention that the size, the estimates, it's hard to figure out exactly how big it is because there's all this dust and gas around it, but the estimates are about 1 kilometer or less, which is a fairly typical comet nucleus size. Okay, so, that's what these things are to the extent that we know, but they are definitely the sorts of things we would be interested in here in trying to go to other stellar systems. There have been people who have tried to figure out, can you get there from here? Flyby missions to either one, either Oumuamua or to Borisov, are at the edge of current capabilities, or they're sort of at the level you can imagine with current capabilities. This group, Hein and Hibbard, did one paper each about each object, and in each case they concluded we could, well, particularly if we knew in advance that we were going there, which we didn't, we could get there with a launch from, it'd take a pretty big rocket like an SLS or a Falcon Heavy, which I would remind you is roughly the size and aspect ratio of Oumuamua. But then that's not enough to get there. We'd need some kind of a gravity assist. They talk about a solar Oberth maneuver, basically a powered gravity assist real close to the sun, close enough that you'd have to use like Parker Solar Probe technology, because that's the only spacecraft we ever had that has gotten that close. And then one more powered Jupiter gravity assist, and we could get there in 10 or 20 years. This is not easy to do, in other words. Another way to do it is to have a head start. Seligman and Laughlin suggested have a spacecraft ready to launch. You see one of these things, you take off, and you might have a chance per decade. Having that Falcon Heavy just sitting there waiting, that might be a little tough. Well, actually, it might not take a Falcon Heavy to do this. But there's actually a mission coming up that might have a shot at this. It's called Comet Interceptor. Colin Snodgrass is the PI. It is an ESA-approved mission to launch in 2028, park in the Earth-Sun L2 Lagrange point, and just wait for, it was designed as a Comet Interceptor, but when these guys came along, Colin said, we could go after these guys too, and do a quick flyby with Comet Interceptor. Of course, these are all flybys, and these are going to be quick flybys, and they're going to be kind of tough. For instance, for Oumuamua, you're going to find a 100-meter object at 50 AU from the sun, and it doesn't have a coma or anything like that. That could be tricky, but if you could get there and rendezvous, there would be a huge payoff. You could get far better imaging than just snapping a couple of pictures going by. If you could actually rendezvous, you might be able to do something like gamma ray spectroscopy or something like that to find out the composition, find out the mass, find out the gravity field, to find out what the interior is, all sorts of things. But you've got to find a way to slow down from, these are things that are coming in. You're guaranteed to have an encounter velocity of like 30 kilometers per second. So it's going to take some kind of advanced technology. That's where, in some ways, that becomes more interesting here. Because when people have talked about this, some of the papers even mention, well, some of the technologies that are being proposed for interstellar missions. So in a sense, if we want to go see these interstellar objects, it might be that the kind of technologies we need to get there and do something useful might be some of the technologies that we need to do interstellar missions to visit their bigger cousins, the planets. And I believe that Jeff Grayson is going to be talking about some technology that could get us even to Oumuamua, which, that guy is moving so fast and so far gone that it's tough, but even with that, could get there. So, to conclude, presolar grains and interstellar dust, they are valuable. I love them, but they don't tell us much about other planetary systems. On the other hand, these macroscopic interstellar objects have a lot of potential. The two we've seen so far do not fit into boxes that we know, which even makes them more interesting as far as I'm concerned. We are starting to find them. We're going to be finding more of them. There's a big telescope project going online called the Large Synoptic Survey Telescope, LSST, that will probably be better at finding these. There's a space-based infrared survey to look for asteroids that I think the press release will be coming out in the next few days saying that's ready to go in about 5 years. That again has a chance of finding things like this. So we're going to be finding more of them. But the missions are difficult. On the flip side, and in a sense, to the positive side, those missions become more possible with the kind of technology that you want to develop to go to other stellar systems. So I will stop there and take questions.
Somebody has to ask, is it a light sail?
Is Oumuamua a light sail? Well, can't prove that it's not, but as far as I'm concerned, there's really nothing that pushes you toward that conclusion. The aspect ratio is a little strange, but it's a shard. I mean, it's consistent with a shard. There are non-grav forces, but then they are the kind that you would expect if it was a body that was outgassing a little bit. The spectrum, well, it looks like something sitting in the outer solar system, or formed in the outer solar system. It does not look like paint. But then again, as I think it was Jeff pointed out, well, maybe it's been floating around for enough billions of years that it's gotten coated by the tholins, so it looks like that stuff. I don't know. I think you have to push hard to make it a light sail. Sorry.
we're seeing them sort of right on top of each other in terms of time for us, right? Are they coming from the same place? Are they 1-2 missions?
Uh, they are coming from different directions. Yeah, so they are in very different orbits. They're not pieces of the same thing. Let's put it that way. And the next one could come from anywhere.
Well, let's end here and thank our speaker again.